we wrote the equation for CAF2. We wrote what the KSP was, and then we reminded everyone that the solubility, whenever they ask you to solve for it, is always equal to X. Now, if we were to write the KSP expression, can you write the KSP expression to the right underneath where the KSP number actually is? Yeah, so let's throw out, we also call it the law of mass action. You guys write can she write the KSP there? And you guys kind of follow along with me. And again, man, I'm just off my game. So you guys have been looking at me again. I'm not presenting her. Thank you. All right, so all that I've been talking about, that's right there. Can you write equal? Can you write that equal to the 4.0 times 10 to the negative 11? And this is kind of a big deal, and I want you to understand how this works. So it doesn't matter how much CAF2 you throw into a container. The F minus squared plus CA2 plus must always equal 4.0 times 10 to the negative 11. Can you draw like a kind of a big beaker in the middle of the board? Doesn't have to be a good beaker, but just a good sized beaker. Can't see what you're drawing, but okay. you made a little lip on the edge. That's awesome. All right. So in that, can you write CA2 plus and F minus? Just somewhere randomly, CA2 plus and F minus. Wonderful. And then in the space somewhere there, can you make like a chunk, just a solid chunk that looks kind of like a chunk of something. So just like a chunk. Just make a chunk of something. Beautiful. Perfect. All right. So right now, can you write CAF2 in the middle of that chunk? Now, let me emphasize this because this is this important. Can you underline the 4.0 times 10 to the negative 11? That is the KSP for CAF2. It cannot be reasoned with. It cannot be changed at a particular temperature. Can you do me a favor? Where it says KSP at the very top in red, can you write at 25 degrees Celsius? Because all of the KSPs and everything we're working at right now is at 25 degrees Celsius. I should make the disclaimer, as I often do, that KSP is only the KSP at a particular temperature. So we're at 25 degrees Celsius. But what that means is this. It doesn't matter. Can you put your finger on the chunk of CAF2? Okay. It doesn't matter how big that CAF2 chunk is. When I take the Ca2 plus concentration and the F minus concentration, and I follow that equation, it must always equal 4.0 times 10 to the negative 11. Always. So let's make the CAF2 chunk, make it a lot larger, if you would. Okay. Do you understand that right now, even though that CAF2 became bigger, it doesn't matter. The Ca2 plus times F minus concentrations that make up that 4.0 times 10 to the negative 11, that will stay the same. Can I get a thumbs up if that makes sense to you? On a more practical level, if you look at our equilibrium, isn't CAF2 a solid? And solids don't impact our equilibrium in any way. True story? Okay. Now, if you would do me a favor here, I want to read with you on page 760 just briefly. Right underneath where it says KSP is equal to Ca2 plus F minus, right next to the delightful picture of the lower gastrointestinal tract using barium sulfate. Okay, it says this. The constant KSP is called the solubility product constant, or simply the solubility product. Since CAF2 is a pure solid, it's not included in the equilibrium expression. The fact that the amount of excess solid present does not affect the position of the solubility equilibrium may seem a bit strange. More solid means more surface area exposed to the solvent, which seem to result in greater solubility, but this isn't the case. Because when solids in the solution reform the solid, they do so on the surface of the solid, thus doubling the surface area of the solid. Not only doubles the rate of dissolving, It also doubles the rate of reforming the solid. So just so you're aware, it does not matter ever how much of the solid you throw in when you're dealing with your equilibrium. Now, right above, it's a paragraph above the problem down below. It says it's very important to distinguish between the solubility of a given solid and its solubility product. This is incredibly important. The solubility product is the equilibrium constant and only has one value for a given solid. Solubility, on the other hand, is an equilibrium position. You know what code word is in our brains we think of? We say solubility product is equal to X. Can I get a thumbs up if you just automatically think that now? Solubility product is equal to X. Now, here's what I want you to do just for practice. Autumn, you're going to be kind of the guinea pig on the board. I want you to write the interactive example 16.1 on the board, and I want you to solve. I want everyone else to do that simultaneously on your own. It's good for you guys to get in the habit of working through these problems. I'll erase everything. And then just write copper 1 bromide has a solubility of 2.0 times 10 to the negative 4. It's actually copper 1 bromide with CuBr. They give us a solubility, don't they? Solubility equals 2.0. Let's leave it so that you can write ice underneath it. Let's write it to the right hand side. Just write solubility equals 2.0 times 10 to the negative 4 molar. Everyone, what does solubility mean again? Always? I see you guys making a cross. Isn't always equal to X? So let's do this. If they give us the solubility and they ask us to solve for KSP, right? Can you write underneath the write it to the right-hand side? Can you write the KSP expression? Yeah. Wonderful. Can we do the ice problem now underneath the CuBr? Just write ICE to the left of like you normally would. Yeah, perfect. And then we're starting off with 0 and 0 of the Cu plus and the Bo minus. And do me a favor, can you put a line through? Yeah, just put a line right there. What's my change going to be? Good. Can you do me a favor? You're absolutely so what she's doing here is 100% right. You're absolutely correct. But can you just do me a favor? Can you just write E as the E place and just make it X and X? Just so you know, what you did is not wrong. You're absolutely correct. But I just want to get you in the habit of doing the things the same way. So then can you plug those X's back into our KSP expression? And since we know what X is, then we can do what she's doing right there. Absolutely. And let's just plug that in and solve for KSP. And if I'm not mistaken here, I'll just jump to the end here. The KSP that you're going to get is 4.0 times 10 to the negative 8. Yeah? Any questions on that? Again, we did this last class period. I'm just doing a brief review on this. Let's also do let's do it the flip way. Let's give you the KSP and ask you to solve for the solubility. So let's do interactive example 16.3. You can find that on page 763. And let's go KSP for CuIO3 in parentheses 2. So we're doing interactive example 16.3. If you just want to write the problem down, please. Me encanta que estás hablando español con él. Okay. Well, the cool thing is once you've done a couple of these problems, they're all going to look very, very similar. You're good, Autumn. Keep on going. Hold on 1 second. See the coefficients of 2? Yep. I'm kind of glad you made that mistake because that's the number one mistake students make. The coefficient actually impacts the number of our K, of our X. Autumn, are you muted right now? Autumn? Can you unmute?
Yeah.
Okay, so are there some people that are listening through their speakers? Because that's the only reason that we have that. Okay, because I want to have some feedback if I can. Everyone, now make sure you have your headphones in. Turn off your actual speakers.
Okay. Well, it wasn't doing anything before.
0.0033.
Yeah.
Yeah, 0.0033. You can hear the squeak.
Okay, so I'm gonna backtrack. One of the things I asked you guys to do last class period was I asked you guys at the very end to compare the relative solubility. So I'm gonna present my screen just for a second. By the way, that's correct. And hopefully you guys can see this. Yeah, there we go. I'm gonna share. And I'm gonna go to. Go to this. So this is what we did last class period, but I just want to reiterate this and before I move on to new content. So one of the things that we talked about is the relationship between KSP and solubility. And the only way you can compare KSPs to each other is if you have each of your ions breaks apart, or each of your compounds breaks apart in the same exact number of particles. So all of these, AgI, CuI, and CaSO4, they all break apart into 2 particles. Which means that if I were doing a KSP equation, this would be x squared is equal to this, x squared is equal to this, x squared is equal to this. So since they're all x squared, then I can look at the KSPs directly and go, oh, this is 10 to the negative 16, this is 10 to the negative 12, this is 10 to the negative 5. The 10 to the negative 5 KSP KSO4 is going to be much more soluble than the 1.5 times 10 to the negative 16. Only because all of these are x squared. Now, let's skip down to this right here. This is kind of a big deal. If you look at these KSPs, you might be inclined to think, oh man, this KSP 1.1 times 10 to the negative 73, that's clearly going to have the lowest solubility. But you cannot compare these three because if you take a look at this top one here, see that breaks apart into 2 particles. This breaks apart into 3 particles. This breaks apart into 5 particles. So if we were doing the actual KSP expressions, this KSP right here on the top would be equal to x squared. This KSP right here would be equal to 4x cubed. This right here would be equal to something that's bigger, like to the 6th or something with other numbers. So if you actually do the math, and this is kind of a cool thing, the BI, and if you take a look on page 765, at the top of the page is the table that lists the actual solubilities. And crazily enough, the actual solubility of Bi2S2 is 1.0 times 10 to the negative 15. Ag2S is 3.4 times 10 to the negative 17. And CUS is 9.2 times 10 to the negative 23. So the reality is that this here, its X value, when you calculate it out, is actually bigger than the X values of these other 2 things, which means that this has the higher solubility. So you need to be a little bit careful whenever you're trying to compare solubilities by be careful of just looking at the KSP. The only time you can compare KSPs for solubility is when you have the same number of particles of each one that they're breaking up into. So here, where all these break apart into 2 and they all would be x squared, we very easily could compare the KSPs. Here, if you look at it, there's no way we can, even though the negative 73 seems really, really, really small, and it is. In order to figure out the solubility, you have to solve for x, and solving for x is really dependent on what the coefficients are when you write the equation out. Can I get a thumbs up if that makes sense? Okay, so now what I'm going to do is I'm going to shift. I should be back on Autumn again. No, what that means is the more particles they break up into, more likely if the KSP is the same, the more particles they break up into, the higher your value of x most likely will be. So there's not a perfect correlation between the 2 of those things, but yeah. So I want you guys to turn to, in your textbook, turn to page 765, and we're going to talk about the common ion effect. And okay, I want you to erase everything there, and I want you to write the equation Ag2CrO4. Let's use like a black, if you don't mind. Am I presenting Autumn right now? Can you verify?
To yourself. I mean, like, it's your face.
You see me, but can everyone else see Autumn? Okay. All right, so let's write the equation up above like you've been doing before, and let's make it as Ag2CrO4. And then is that equilibrium with? Two Ag plus? Two Ag plus CrO4 2 minus. Okay, and the KSP for the Ag2CrO4 is 9.0 times 10 to the negative 12. Okay, I want to do a proof of concept with this. Can you hold on a second here. Can you solve for the solubility of that by itself? Just solve for the solubility. Okay. So would you be okay with saying that that's the solubility of the Ag2CrO4? 1.31 times 10 to the negative 4. Now watch. What we're going to talk about right now is something called common ion effect. So if you look up above, in these cases, in all the cases where we've been asking you to solve for the solubility, we've been starting off with 0 of the ions in solution to begin with. But what if we don't start off with 0? What if we start off with some ions already in the solution? Now, can you do me a favor? Can you actually write the law of mass action to the right up above of the equation, right above where you, yeah, right in that space right there. Can you write KSP is equal to Ag plus squared concentration times concentration of CrO4 2 minus? And can you write that equal to 9.0 times 10 to the negative 12? So would you acknowledge, can you put your finger on that KSP expression you just did? Okay, right there, do you understand that no matter what our Ag plus and our CrO4 2 minus concentrations are, when we multiply them together, they must equal 9.0 times 10 to the negative 12. Now, in all the cases that we've been dealing with so far, since we start with 0 of both of them, at the end, we have the same exact concentration of both of those things to make the 9.0 times 10 to the negative 4. But let's just say I were to dump in a bunch of Ag plus. Wouldn't the CrO4 2 minus concentration have to go down a lot? Because that 9.0 times 10 to the negative 12, it can never be changed. Are you guys understanding this? So whenever you have that KSP expression and you have actually a value of 9.0 times 10 to the negative 12, if you have that value, no matter what changes with one of those two variables, either the Ag plus or the CrO4 2 minus, the other one has to adjust to keep that expression. So for example, let's just do this in our heads. Let's put your finger on the Ag, the actual reaction. Okay, so let's say that reaction is at equilibrium. Doesn't that mean that the forward reaction and the reverse reaction are going at exactly the same pace? They're equal to each other, right? But what would happen, according to Le Chatelier's principle, if I were to dump in a bunch of Ag plus? What would happen to the equilibrium? Wouldn't it shift to the left-hand side? And wouldn't that mean that less of the CrO4 2 minus will be dissolved as well? So what we do often in these problems, and this is the new normal, is going to be this. Instead of starting off with just the solid that we throw into water, what we'll do is we'll throw that solid into water and there will already be an ion sitting in solution waiting. So let's do a problem like that. So let's say in this exact case, let's say we're throwing in Ag2CrO4 into a 0.1 molar, so right up above. Say, what is the solubility? So question mark solubility of this of Ag2CrO4 in a 0.1 molar solution of AgNO3. So what is the solubility of AgCrO4 in a 0.100 molar solution of AgNO3? That's right, 0.100 molar solution of AgNO3. AgNO3. Now, here's what you need to be aware of here. When I say that I'm throwing that into a 0.1 molar solution of AgNO3, isn't that the same thing as saying a 0.1 molar solution of Ag plus and a 0.1 molar solution of NO3 minus? And we don't care about the NO3 minus. All we care about is the Ag plus, because isn't Ag plus part of our overall equilibrium? So what I want you to do is this. I want you to erase what's right underneath the Ag plus in your I expression. In your ice, right underneath the 2Ag, underneath the 2Ag, yeah, that row right there, just erase that row. The column, not the row. That there, perfect. Okay, now watch. What they're saying is that they're throwing Ag2CrO4 into a solution that already has 0.1 molar AgNO3. So that means that instead of 0 Ag plus, do you see how we have 0.100 molar Ag plus? Does everyone understand how we got that? Yeah? Now, the change is still going to be plus 2x, agree? Because it's still a but now at equilibrium, we have to add that to the 0.100. Good job. Now, can we do underneath there? Can you write the KSP expression again? And let's just solve using the 1.0 molar plus 2x instead of it being x. Can someone help her with the math there?
Really?
Oh, I kind of wanted you to leave the original solubility just so you can compare, but that's all right. So what do we get for x? 9.0 times 10 to the negative 12. Agree? What I want to do just briefly is when we already have an ion in solution, not as much of the original can dissolve. So in the previous case, the solubility, if I'm not mistaken, didn't we say it was, can someone write down what the solubility was originally? Wasn't it X? On the right-hand side, can you write this down?
Yeah.
X is equal to, what was the X equal to in the first, when we hadn't dropped anything in? Anyone have it?
What was the original one? 1.31? Yeah.
Times 10 to the what? Negative 4?
Yes.
Okay, so do me a favor. Can you underline the two solubilities, the two X's? Just underline them or box them or something. A different color. Okay, so watch. When we had nothing in the solution except for water, and we threw the Ag2CrO4 in there, 1.31 times 10 to the negative 4. Can you put your finger on that up above? That's how much dissolved. Can you put a capital M for molarity because we want to have a unit in there? But when there was already a common ion, when we already had one of the things that's part of the KSB in the equation before we started, only 9.0 times 10 to the negative 10 dissolved. So clearly when there's already a common ion in the solution, not as much will dissolve. Are you all with me on that? Ask me any questions of what we just said. So literally the only difference in the problems we're doing right now is that instead of starting with 0 and 0, we're going to start with a certain amount of one of the ions. Okay. I want you to go to page 766, and I want all of you guys just to do proof of concept. I want you to do interactive example 16.4. Can you do that on the board for me, please, Autumn, as well?
show us the cat.
Is it there? Oh the cat knows you are God.
Well, good.
Oh, look. Oh, he's putting the headphones down. Oh, baby.
Don't.
I have it right here. Thank you.
You have it?
Thanks so much.
That's the thing I should
In about 10 minutes, he probably could use a snack.
Okay, what's the answer?
What do you
Oh, the next is.
Wait, can you? I'm sorry, can you repeat that one?
6.40 times 10 to the -8. You should never do that.
Oh, it's supposed to be only one single
Yeah.
Kayla, will you make me some hot cocoa? Will you make me some hot cocoa?
Hot cocoa for a hot cocoa. No, bro, trust me, I got one.
Okay, that looks so. No. I'm not so well.
That cat is a rescue cat. By the way. All right. Does everyone agree with that value? Okay. Just understand that solubility, that X, is much less than it would be if we didn't originally have the NAF in there. And by the way, I love what she did there. They're always going to talk to you about, hey, CF2 is thrown in a solution of NAF, right? Does the NA mean anything to us at all?
No.
It's a spectator ion, right? So we don't care about it. Now, let's erase everything, and we're going to talk about Q again.
Okay, what?
We're going to talk about Q, or ion product. So can you guys turn to page 768? And Autumn, since you have your textbook there and you're on the mic, can you read starting at the very top of 16.2?
Yeah. So far, hey, I'm reading.
Yes, she is.
So far, we have considered solids dissolving in solutions. Now we will consider the reverse process, the formation of a solid from solution. When solutions are mixed, various reactions can occur. We have already considered acid-base reactions in some detail. In this section, we show how to predict whether a precipitate will form when two solutions are mixed. We will use the ion product, which is defined just like the expression for KSP for a given solid, except that initial concentrations are used instead of equilibrium concentrations. For solid CaF2, the expression for the ion product Q is written. If we add a solution containing Ca2 plus
Okay, actually, do me a favor here. If we wrote that about on the boards, can you write the KSP for the law of mass action for CaF2 to the right up there?
Yeah. Oh, yeah.
Just write the K, the KSP. Okay. So that's at equilibrium. Won't the Ca2 plus times the F minus squared will equal 4.0 times 10 to the negative 11, I think. I can't really read it very well, but I think 10 to the 11. Now, if we are not at equilibrium, then obviously that equation won't work, but we still want to be able to figure out what our values are. So instead of writing K, we write Q. You guys remember us doing this before? Okay. Can you write, right next to the K, can you write KSP, SP down below? Now, I want you to do the exact same thing, write exactly what you wrote, except instead of K, you're going to write Q. So write QSP. Okay, so what you should be aware of is this. The Q, and do me a favor, can you write a little 0 as a subscript next to the Ca2 plus and the F minus?
Right here.
No, on the actual Q expression. Hi, Zion.
What's up?
Now, just so you're aware, anytime you see a little 0 as a subscript, we call that not, and that means initial amount. So what we're going to do is this. Instead of giving us a reaction at equilibrium, what they're going to do is they're going to give us individual ions. So they'll give us the Ca2 plus ion and the F minus ion. And they'll say, will that form a precipitate? Will it form a solid? Now, what you need to understand is this. Put your finger on the KSP, please. Expression. That expression right there. And put your finger on the actual number. Okay. That number right there, that is the maximum amount of Ca2 plus and F minus that we can have in solution before you can't have any more in there. So if you have more than 4.0 times 10 to the negative, is that 10 or 11? I keep on saying it correctly.
I don't think I want that. That's 10 to the negative 11.
Kayla, move out of the way, please.
Sorry.
Times 10 to the negative 11. That's the maximum you can have. If you put any more in there, it will all precipitate out as solid. So what we want to do is this. If they give us a certain amount of ions of Ca2 plus and F minus, if we multiply them together, we're going to get a value. Can you put your finger next to the Q expression? Can you write equals on the end of that?
I'll drink it. You'll drink it.
And then question mark.
I think it will be fine. It's just
So watch. If that Q value that we solve for is less than 4.0 times 10 to the negative 11, let's say it happens to be 1.0 times 10 to the negative 15, let's say, which is smaller than 10 to the negative 11, right? If that's the case, then we know that we don't have enough ions to reach equilibrium and no precipitate will form. Are you guys all hearing this right now? If, however, my Q value happened to be this, wait for it, 4.0 times 10 to the negative 7. Okay, let's say it was 4.0 times 10 to the negative 7. Would you all agree that 4.0 times 10 to the negative 7 is more or greater than the 4.0 times 10 to the negative 11 that equilibrium allows? This is where I need thumbs up because this is literally the important concept going forward.
If more than what? I missed that part.
If our Q value is greater than our K value, it means that we have more ions than the equilibrium will allow, and we will have a solid formed. If we have less ions than the K value, that means that we can still put more ions in before we reach equilibrium. That makes sense? So let's turn to problem on, let's turn to the determining precipitation conditions, interactive example 16.5. And can you actually write the entire problem on the board at the very top?
Yes, sir. I just can't find it. 16.5? That doesn't exist. Oh, interactive example.
I can't wait to see his face when he sees it.
Oh, that whole equation? Is he even listening? He's on mute. Okay. So he wants me to do CeNO3 and KIO?
Unmute him.
He's muted. You're muted.
So write everything out for the actual expression. So write a solution is prepared, adding, and then make sure we have 750 milliliters of 4.0 times 10 to the negative 3 molar CNO3 is added to whatever. Let's write the whole expression across the top of the board, the whole equation, and then we're going to work off of it.
Oh.
Okay. Yeah, so he gets it.
Yeah. 16.5.
Oh, I don't know what that means.
It's interactive example 16.5.
If you fuse,
Lauren, can you read it out to me?
If this equilibrium in your stomach,
by adding
and the key is bigger than here, okay?
of 4.00 times 10 to I don't know what that means.
Watch that.
CE in a
No, I'm just on my own way.
CE in 3
Yeah, my mom says about Brandon. And then
Okay.
200 milliliters.
800 milliliters.
I'm on the same
Like
level.
TO. I don't know my bad. 300 milliliters.
300?
Yes.
Okay.
2.00
Bro, who wants to talk to
times
safe
10 to the
candy before it
negative
leaves
2.
2.00?
Whatever.
Yeah.
That's all wrong. Give it back.
No, it died. My mom
Good.
Oh, no. Did you get 2.0 times 10 to the negative 2?
Mine was 2.
That's still being killed by the because you're wrong.
And then the KSP is 1.9 times 10 to the negative 10.
What happened?
1.9 times 10 to the negative 10.
That's it? Okay, that's it.
Oh, it's asking if
Oh.
CeIO3 3 will form a first.
It's CeIO3?
CE in the parentheses IO3.
Every new vibrate. Willie! OCE. Oh, my arm. Wait, what does that say?
Okay, we got it? Okay. So
It's Will. Will CeIO3.
I like it. It's like Willie.
Yeah.
can you write the actual equation for CeIO3 in parentheses 3? Can you write the equilibrium equation? So CeIO3 in parentheses 3 and make a double arrow.
Be careful.
Parentheses 3. There's a 3 subscript next to that, and it's a solid.
Jackson,
I'm sorry.
Jackson.
Oh my God.
So good.
Jackson hit Karina.
Karina? With what?
Karina just got
Jackson, what did you do? Karina, what did Jackson do?
Jackson abuses women.
Okay, let's lock back in here because we only have a few more minutes and I need to make sure you understand this. So, watch.
That was 11:10.
Everyone with me, please?
We get out 11:10. We got time.
Okay. All right. So, if you take a look at this equation right now, we know what the K value is for that, right? But we aren't at equilibrium. They're giving us initial amounts of both of these, right? So can you write for me on the right-hand side, can you write the K expression? KSP?
Oh, hey, look. I was right on the dime, dude.
Okay. And right underneath it, can you write the QSP expression?
QS.
Okay. I need incredible focus right now. Can you make a little knot next to the CE and a knot next to the IO3, please? Okay. So watch. We want to plug in values. Can you put your finger on the CE2 plus? We want to plug in a value for C on the next to the Q. Next to the Q. Okay. Put your finger on the CE3 plus. We want to plug in the initial concentration of CE3 plus, and we want to plug in the value of the initial concentration for IO3 minus. When we multiply those out, we want to compare what our Q value is to our K. Can you write next to the KSP equation up above? Can you write what the actual K value is?
Hey, look. You gotta. There we go. Jeez, chokes. That went right down the pivot.
Okay, now watch. How do we figure out what the actual concentrations are of CE? I need everyone right now completely focused, looking at me and looking at the board. So watch. Zion, are you focused? You're all good? All right. So watch. In order to figure out the Ce2 plus concentration in the actual equation, doesn't it say a solution is prepared by adding 750 milliliters of 4.0 molar CeNO3? Now, isn't that CeNO3 really the source of the Ce3 plus? Can you underline up above where it says CeNO3 with a different color pen? Can you underline the Ce? Okay. And then can you do the same thing? Can you underline the IO3 in the... Wonderful. So what you have to be careful with on this, and can you, underneath where it's underneath focus, can you write M is equal to NV, N over V? And can you write M times V equals N? M is in Mary.
I don't even know how to do this. M equals N over
Okay, now watch. Would you all acknowledge that we have 750 milliliters of 4.0 times 10 to the negative 3 molar CeNO3? Now,
Okay, huh? What'd you say?
okay, everyone, Jackson, Zion, etc., stop. We have very little time here, and it's incredibly distracting. And now we have this on broadcast for future generations. Okay. What we need right now is we need the Ce3 plus concentrations. Can you write Ce3 plus concentration, like a square bracket? Just write it down below, right somewhere down below there, like right there. It's perfect. Right, Ce3 plus concentration. Okay. Now, would you acknowledge that we have 750 milliliters of 4.0 times 10 to the negative whatever molar CeNO3? Now, the problem is we can't say that the concentration of CeNO3 or Ce is 4.0 times 10 to the negative 4, because aren't we adding 750 milliliters to 300 milliliters? So don't we have a new volume? Are you following me here? Can you do this? Can you write M1V1 equals M2V2? Right next to, like put an arrow next to the Ce3 plus. And can you write M1V1, capital M1V1 equals M2V2? Okay, so this, by the way, is the way we always figure out new concentrations when we change the volume. So would you agree with me? And can we plug in values here? For our original molarity, won't it be 4.0 times 10 to the negative? I can't read it. So is that 3?
11.
And the volume, isn't it 750 milliliters? And we want to solve for the new molarity when we add the two of them together. And what is the new volume?
1,000.
Isn't it 750 plus 300? Okay, everyone pause. Does everyone see what we're doing here? We are trying to figure out the Ce3 plus after the two things are mixed because the concentration will change. So let's solve for the M for that, please. And that molarity is going to go in our QSP equation.
Can someone give me the answer? I'm sorry.
So you guys realize we're going to have to multiply the two things on the left and then divide it by 1,050 milliliters. I'm not a huge fan of the fact that we didn't put any units in there because that's going to allow us to cancel out and end up with molar. Can you write capital M for the next to the first thing? And then can you write ml, milliliters, next to the second thing? And then on the far right-hand side, can you write ml for the 1,050?
No.
It's equal to 0.0029.
Oh, that doesn't seem right.
You said it doesn't seem right.
Oh, actually, sorry, my bad, because it's 10 to the negative 3. That actually works. I like it in exponents if you can. Okay. Now we're gonna do exactly the same thing, but we're gonna do it for the IO3. You do that right, either on top of it or next to it.
One smack per day. Oh, you.
Everyone help her, please do this.
What did you smack? Where it went down.
Oh, by the way, in case for those of you who are cat lovers, this is how my cat sits next to me. Kind of hangs out with me all day. Where's my cat whisperer, Karina?
Have answered.
I made you.
No. Why do you look so angry?
Let's go, guys.
0.0057. That's right.
Is that correct? So now watch. Don't we have the concentrations of both Ca3 plus and IO3 minus at the starting point? We're going to plug both those values into the Q expression over on the right-hand side. And we're going to solve for that, and then we're going to compare that to our K value.
What are you doing?
Just take a picture of this.
Yeah. I don't want that. Nope. Stuff.
Yo, what if we put the gun over there, like on the overhead? It's 1.65 times 10.
So the negative 9.
Got a better response than the first time.
Tienes 5 minutos.
Okay, now really quickly here, it's really hard for me to read. Does this Q say 1.65 times 10 to the what?
Negative 5.
Negative 5.
Yeah.
What is our K value?
1.9 times 10 to the negative 10.
Which is bigger?
QSP.
Q. Now listen carefully because this is the tying it all together. If our Q expression is bigger than our K, it means that we have more ions than the water can actually hold, which means a precipitate will form. So right, QSP is greater than, so do QSP greater than symbol KSP, precipitate will form.
How about you? Stop. Stop. I'm getting it from everybody, every angle.
Any questions on that?
5, 6, 7.
Any questions?
Okay. Now, there's one more level of difficulty past this, but I'm going to pause right there. And I'm going to have you guys practice on a few of these. So at the end of chapter 16,
Don't say thank you to that. Don't say thank you to that.
you guys do problems 49.
49. Oh.
British.
So was I.
Autumn, can you write the top?
Judgmental to that.
I asked you.
49,
through 56.
49, 56.
Yep.
For homework?
For homework. And you have about 5 minutes, 6 minutes left. I do not want to jump into the next topic. I'm going to hopefully be with you guys next class period, and I'm going to that's very sad, Kayla. That's very funny. Oh, that's not funny at all.
Whoa. Like it.
Write that on the board for everyone here. So chapter 16, problems 49 through 56. The remaining 5 minutes, I want you to work on that or start working on it. And that is all. I will see you guys on Monday. So, oh, by the way, we're going to have a test probably the end of next week.
What?
Yeah. So, yeah. We'll have class Monday, Wednesday, and then most likely we'll have the test on Friday. So yeah, and we also have to do a lab. Water and gas are finally back on in our room. Let me turn off the broadcast.